Okay, today we're going to be learning about solving systems of linear equations by graphing. I know I've got it when I can determine if an ordered pair is a solution of system of equations in two variables, solve a system of linear equations by graphing, and without graphing, determine the number of solutions of a system. Q vocabulary is a system of linear equations. That means two or more linear equations. A solution to an equation is where two lines meet. Consistent system has at least one solution. Inconsistent system has no solution. Independent equations are just equations that are different. They're independent of each other. And dependent equations are equations that are different, that are identical. They depend on each other. So a system of linear equations consists of two or more linear equations. This section focuses only on two equations at a time. You'll do 3 in Algebra 2. A solution of a system of two equations in two variables is any ordered pair of numbers that is a solution of both equations in the system. So in example 1, we're going to determine whether -3, 1 is a solution of the system. So we're going to do that by plugging in numbers, plugging in the -3 for the x and the 1 for the y in both equations and seeing if they have true statements. So you're going to say -1, -3 for your x minus y, which is 1, equals -4. And that is a true statement, but you have to also check the other one. So 2 times -3 plus 10 times 1 equals 4. So -6 plus 10 is also a true statement. So you would say, yes, they are the same. So you would say, yes, -3, 1 makes both equations true, so it is a solution. All right, number 1b says determine whether the ordered pair 4, 2 is a solution of the system. So we're going to do the same thing. We're going to plug the 4 in for the x and the 2 in for the y. So I'm going to say 2 times 4 minus 5 times 2 equals -2 and see if that is true. And we see that it is. Then I'm going to do the second equation. So 3 times 4 plus 4 times 2 equals 4. So I'm getting this from my x and my y. So I'd say 12 plus 8 is 20, not 4. So no, it is not a true statement. So it would not be a solution of the system because it doesn't make both equations true. Okay, so you go ahead and do this one. Go ahead and pause the video. And you should see that no, it is not a solution. So if we want to estimate the solutions of a system, we can graph each equation on the same coordinate system and estimate the coordinates of any point of intersection. So solve by graphing, you're going to actually show where the two lines meet. Okay, so you can graph this several different ways. I'll show you two different ways right now. Okay, so you can do it at slope-intercept form, or you can do it using intercepts. So I'm going to do the first one using intercepts. We'll just try this. So if I wanted to find the y-intercept, I would plug a 0 in for x. So when I do that, I would get my x-intercept is -6. And if I did that to find my x-intercept, I would find that it equals 3. So I would put a dot here, a point there, sorry, and a point here. And then I could join the two coordinates. Okay, now let's do the next one. So I did this one using intercepts. I'm going to show you how to do the second one using slope intercepts. So I've got x plus 3y equals 10. We want to get it in y equals mx plus b. So I'm going to subtract the x from both sides and divide by the 3. So I would get y equals -1/3 x plus 10 over 3. Now if I graph that, that's at 3 1/3. So 1, 2, 3 1/3. And you can see why we say we're estimating, because that is definitely an estimate. And I'm going down 1 over 1, 2, 3. And then, sorry, down 1 over 1, 2, 3. So if I wanted to do this, let's see, let me graph that line. I'm just going to put those as close together as I can. And so if I had to estimate, my best estimation would be right here where they're intersecting. So I would say at 4, 2. And that is the correct coordinate. All right, 2B, it says solve the system by graphing. If it has just one solution, estimate. Okay, so we're going to do this. Again, you can use intercepts or slope intercept, either way. So I'm going to go ahead and use slope intercept to get y'all in the hang of that. So the first one, I'm going to go ahead and move the x to the other side and divide by 3. So 6 divided by 3 is 2. And then I'm going to do the second equation. So I'm going to subtract the 3x from both sides, and I would get negative 9y equals negative 3x plus 9. Divide everything by a negative 9, and I get y equals 1/3 x minus 1. Now, if I graph those, what's going to happen, you will see that they are parallel lines. So if the solution is where they touch, and then in parallel lines never touch, then there is no solution. And the system is said to be inconsistent because it has no solution. All right, you go ahead and do this one. Pause the video. So when you do this, you should have gotten the same line. And when you graph these equations are said to be dependent equations because they're the same equation on top of each other. So there's an infinite number of solutions to the system. So if you were doing this in class, you could say infinite solutions or all reals. All right. So there are 3 possible outcomes when graphing 2 linear equations in one plane. One point of intersection, so it would have one solution. Parallel lines would be no solution. And coinciding lines mean the same line on top of each other, so an infinite number of solutions. If there's at least one solution, the system is considered to be consistent. And if the system defines distinct lines, the equations are independent. And so that's what it would look like. So you would have one solution connecting right here. If there's no solutions, if it's parallel, or if there's literally 2 lines on top of each other, you'd have an infinite number of solutions. So this would be, if it has one solution, it's considered consistent independent. Consistent independent. If they are parallel, it's an inconsistent system. Inconsistent. And if you have the same line on top of each other, you would say it's consistent dependent. Since there are only 3 possible outcomes with 2 lines in a plane, we can determine how many solutions of the system there will be without graphing the lines. You can change both the linear equations into slope-intercept form, and then we can easily determine if the lines intersect, or if they're parallel, or if they're the same exact line. So if you have 2 different equations, they're going to intersect and have one solution. If they are parallel, so same slope, different y-intercept, they're not going to have any solutions. And if it's the same exact line, of course, there will be infinite solutions. So number 3, without graphing, determine the number of solutions of the system. All right, so we need to put these both in slope-intercept form. So I am going to just subtract 3x from both sides, and I would get y equals negative 3x plus 1 for the first one. For the second one, if I subtract 3x from both sides, I would get 2y equals negative 3x plus 6. And then if I divide everything by 2, I would get y equals -3 over 2x plus 3. So as you can see, these have completely different slopes. So we would say that they are intersecting lines and there's only one solution. So this would be consistent independent. Consistent independent, and they have one solution. All right, 3B, without graphing, determine the number of solutions to the system. So same thing, we're going to put these both in slope-intercept. So I'm going to subtract 3x from both sides. So I get y equals -3x. And over here, I would have to divide the 2 to isolate the y, so I get -3x. What do we see? The two lines are identical, so there are infinitely many solutions. So if you were classifying this, this would be consistent dependent, because the lines are the same. So literally they are depending on each other and they have at least one solution. They have infinite solutions. So it's consistent dependent. All right, 3C, you go ahead and try this one. And you should see that they're parallel, so they have no solutions and the lines are inconsistent, because both of the slopes would be -2 and you have different y-intercepts. All right, so you can go ahead and pause this and get some extra practice in. So the first 4 are like the first example that we did. You're plugging the numbers in and seeing if they are true for both statements. 2, you're solving by graphing and estimating your solution. And 3, without graphing, determine the number of solutions. So go ahead and pause it, and then you can see in a second what the answers are. All right, here you go. There are the answers. Please let me know if you need extra help. So the success criteria for this lesson is I know I've got it when I can determine if an ordered pair of is a solution of a system of equations in 2 variables. So determine whether the ordered pair is a solution, solve a system by graphing, and without graphing, determine the number of solutions it has. So if it's parallel, it has none. If they're different equations completely, it's 1 solution. And if it's the same exact equation on top of each other, it's infinite solutions. But do you really understand? So the solution to a system of 2 equations is -3, 5. What must be true about the graphs of these 2 equations? How can you check the solution algebraically? The graphs have to intersect at that point, and you can substitute -3 in for x and 5 in for y in both equations and check that the resulting equations are true. Give an example of a system of equations that has no solution. Explain how you know it has no solution. Anytime the slopes are the same and the y-intercepts are different, the lines are parallel and therefore have no solution.